Yesterday we left off talking about isotopes, which were different variants of each element that have a slightly different number of neutrons and therefore a slightly different atomic mass. Now I left you with a way of showing isotopes by simply writing the atomic mass of that specific variant of the element as a number to the right of the name, separated by a dash. And this is fine, this works, but it's a very long format to show a very small amount of different information. So I want to show you one other method to represent isotopes. And I'll show the same three isotopes, carbon-12, carbon-13, and carbon-14, here on the left. Now, to write out a condensed isotope formula, an isotope symbol, what you're doing is very similar to how we showed ions with just a symbol, where we had just the number of the charge attached to the symbol itself. So all of these start with the same thing. We start with the symbol for our element, in this case, carbon. Now all of these are carbon. They have the same number of protons. And we show that by showing their proton numbers here on the bottom. 6 protons for each. But for each variant that is a different isotope, we show a slightly different number for its atomic mass, which we show in the top left, above and to the left of the symbol. In this case, carbon-12 would be C12, carbon-13 would be 13 over 6C, and carbon-14, our unstable isotope, would be 14 over 6. So, key ideas to remember here. This is simply our symbol from the periodic table. This hasn't changed. The number on the bottom left is our atomic number. And the number on the top left is our atomic mass of the isotope. And that will change for each and every isotope variation we discuss. So make sure you're taking this down because we are going to use this format much more than this because this just takes too long to write. And we're always in a rush. The shorter the time we take, the better it is. So what we're discussing using these symbols is I want to talk about the 3 different ways that an unstable isotope can undergo decay. Now when I say decay, I'm not talking about it becoming some sort of rotting zombie isotope, some rotting zombie version of the element. What I'm describing here is that the element will actually break down. The nucleus is so unstable, the way it's been attached, that it will start to fall apart. And it can fall apart in one of 3 ways. So decay, the general idea, and I'm going to clear off the rest of the board so we have some space to work with, can be shown in this way. Isotopes decay. They break down into a series of products that are formed from the same building blocks as the atom. We are still governed by conservation of mass. You cannot create or destroy matter. You can simply move the pieces that make it up around. Well, before we talked about this as moving around electrons. Well, now we're talking about the neutrons and the protons. We're talking about the nucleus, which is fundamentally more difficult to reach, which is why this only occurs in unstable radioactive isotopes. So we have 3 different kinds of decay, and this happens when an isotope breaks down. We can get one of 3 products. We can have what we call alpha decay, beta decay, or gamma decay. Now, these 3 types have 3 different products. Alpha decay is the production of what we call an alpha particle. And an alpha particle is similar to a helium atom's nucleus. So an alpha particle, which we show with the Greek symbol for alpha, which is this little fish-like symbol I've shown you before, the alpha particle has, in this case, a mass of 4 and 2 protons as part of it. Now we also will occasionally show this as 4,2 helium to show its connection to a helium nucleus. A beta particle is different though. A beta particle is one of those places where we can actually form more protons. And the symbol for this is a 0, -1, and then the symbol for beta, which is like a bee with a tail on the end, just here. Now, why that happens is a tricky one to explain. Because what we describe as subatomic particles are the smallest pieces we work with in Science 10, but it is not the smallest pieces, the smallest building blocks of atoms known to science. Each subatomic particle, protons, neutrons, and electrons, are made up of smaller pieces, which you may have heard of as things like quarks and leptons and muons and so on. Now that is way beyond the scope of our course. So when we talk about beta decay, we can't avoid briefly mentioning these ideas because these particles are breaking apart. We're actually destroying a neutron and splitting it into two pieces as a result. So beta decay we'll discuss in a bit more detail momentarily. And our last form of decay is actually the release of a high energy particle, which we show as 0, 0, the symbol gamma. So let me show you the different ways that we'll see this type of decay taking place.